Good evening, everyone. I am Akshita Sharma, your presenter from IIT Delhi, is going to discuss weekly problems and concepts in the course Nanotechnology, Science and Application. And if you have any doubt during the session, you are free to raise your hands and ask the question. Uh, this is an interactive session, so I request everybody to be to participate in the session, so it will become more interactive and help you in learning. So let's begin with the today's lecture. So in the last class we have discussed various type of techniques, how to make nanoparticles and how to understand the vapor plasma technique. So we are understanding how the magnetic properties of nanoparticles and how they different from bulk. So that's the thing we are discussing here. So moving on to the first question, what are the question the one is, what are the condition for ferroelectricity? There are basically two conditions for ferroelectricity. One is the charge neutrality. Okay, that means the number of positive and negative charges should be balanced. Okay, second condition. So understand the second condition and then we will understand through an example. The centers of positive and negative charges are not this is the main part, not coinciding with each other. And the best example to understand both the condition is barium titanate. Who will explain me these two conditions on the basis of using an example of barium titanate? Anyone? So barium titanate is a body centered we understand through a unit cell. We have a big barium atom Ve2 plus, and here we have titanium 4 atoms. Sorry, this is barium. These are barium atoms, and these are titanium plus 4 atoms. And on the face centered, on the faces of we have oxygen atoms. Okay. Now, if we considered it is in a top view, if we see the material from the top view, then how will we see it? We'll come to next second question. But let me explain you the two conditions first. How does it matter? Now we have these. Okay, can I change? No, cannot. We have this. We have this. We are seeing these portion. Okay, so only 4 atoms we are considering. Now this will appear. This atom will appear. I'm keeping it as empty. The one body center atom will be below it, right? Somewhat here, which is smaller. And now we'll see these phase standard atoms from this view. So it will appear like this. I just dotted it for your reference. Similarly, this view we have. Okay. So this is falling above this center. This is falling above this center. The center of positive is coinciding. This is coinciding. This is coinciding. These are also coinciding with each other. But if you see from this point of view, you will realize this atom, center of this atom is not coinciding with this atom. And this is an atom of O2 minus, and this is titanium 4 plus. And since the center is not coinciding, then the moment is not zero. The dipole moment which is produced is not zero, and hence is a creation of polarization. Okay, so this is the condition for the ferroelectricity, and then we see this material behave as a ferroelectric material. Hope you have all got this. Now, second question. So, on understanding the condition of ferroelectricity, now there's a time to move on the application part. There are basically there are many applications, but the most prominent are two applications. The usage of ferroelectric material in LCD displays, that is liquid crystal displays, and another one is data storage. In the data storage we have, like, we know the dipole moments are in have upside down, one is upside and one is downside, and these can be treated as 0 and 1 bits. Okay, and in this form we know data is being stored, and hence data can be stored very well. And also, when we use ferroelectric material in data storage, ferroelectric material, then it uses less power than ferromagnets. Okay, this was all about what are the conditions, what are the application, and how does it work. Next question. Ferroelectric material has, we have to see which of the option is correct. Option 1, high dielectric constant which varies non-linearly, low dielectric constant and non-linear, high dielectric constant which varies linearly, or low dielectric constant and it is linear. Which of the option is correct? Correct option is 1. Okay. High dielectric constant which varies non-linearly. Now, next question. Plot polarization versus electric field for ferroelectric material. For ferroelectrics, we can say. Now, you need to understand, we have understood that there is a generation of polarization in ferroelectric material. How does it behave? If I considered this is P polarization and this we have electric material. This option is correct. Now we are starting. It has some when it is behave like sigmoidal shape. So let me draw it very carefully now. We have this kind of shape, P and electric field. This point is called saturation point. Beyond this, there is no change in the polarization. This is called reminiscence, which means remaining polarization, because now electric field is 0 but we still have some polarization. And the amount of time which it take from moving from one point to this time, one point to another point, coercive force. So this is a plot we have understood, and this give example of ferroelectric material. Next question. We have first example BiTiO3, barium, titanate. Second example, lead, zirconate. that is called lead zirconate titanate. Its short form is PZT. Third example. Okay, let me do it here only. Lead titanate, that is PbTiO3. Fourth example. Lead lanthanum zirconate titanate, that is PlZT. Lead lanthanum zirconate. See the position of this element in the periodic table. You will become more familiar with the periodic tables. Next question. Classify the ferroelectric materials. We can classify the ferroelectric material in n number of ways. So before moving on to this question, we will understand this question first. So it will be easier for us to correlate. I've shown you how does a plot versus polarization versus electric field look like. Now you have to plot how does soft ferroelectric and hard ferroelectric behave. So we need to see how does it behave in the presence of electric field. That's it. Soft ferroelectric means that it will have smaller polarization with a small change in electric field, whereas the higher polarization with a small change in the of electric field, whereas in the hard ferroelectric there will be low polarization with the same amount of electric field as applied in the soft ferroelectric. So the plot will look like for the soft one it will look like like this. It will be very sharp. This is smooth, this part is smooth, this part is also smooth. Okay, everything remains same. Plotting on this value only, another axis, this is 0, this is 0, this is not passing from 0. Okay, and for this it will look like we have to make larger polarization. Do you understand the difference? The remnant polarization may be same, but the coercive force is high. This is hard, this is soft, it is very large in case of hard ferroelectric. Now, next question. Classification of ferroelectric material. We can classify the ferroelectric material on the basis of various properties. So we will see one by one. First, and I will tell you the examples side by side. First is crystal chemical composition. The examples will be same sometimes because we are just classifying on the basis of properties. Okay. Crystal, this is another classification. Crystal structure, third. Symmetry, on the basis of symmetry we also classify symmetry related thermodynamic behavior. Fourth, structural change during phase transition at TC, Curie temperature. Okay. And another is, maybe so we'll look on to these only, these example only. This can be further classified hydrogen bonded composition. The example is Rochelle salt, which is a calcium dihydrogen, potassium dihydrogen phosphate. Ignoring this question, now we have already covered this. Double oxides. Barium titanate, potassium niobate. On the basis of crystal structure, corner sharing oxygen octahedra. Okay. Example, barium titanate, share oxygen. I should not write over here. So if I make another unit cell over here, so it will be sharing the corner with the another unit cell as well. Another is charged order ferrites, Fe3O4, or we can have another ferrite, copper Fe2O4. Same, we have doped, we have substituted one of the iron atom with the copper. Okay. On the basis of symmetry, we have two other subclassification. Non centrosymmetric non-polar. Non-polar. Another is centropolar. Another example, order, disorder, and displace type. Okay, so somebody is asking, what is Reshol salt? The chemical formula of Rochelle salt is, it is a salt of sodium, potassium, and we have, I think, some group of oxalic acid with hydrated water molecules. Okay, and the transition temperature for it is minus 10 to 23 degree Celsius. In this range, it behave as an ferroelectric. Got it? So we have at least four and we can classify ferroelectric material in four ways. One, on the basis of crystal chemical composition, which itself has two sub classification: hydrogen bonded composition and double oxide. Okay, which has example of Rochelle salt and potassium dihydrogen phosphate. And under the double oxide, we have examples of barium titanate and potassium niobate. Second, we have crystal structure, which has corner sharing oxygen octahedra, barium titanate, and we have charged order ferrites Fe3O4 and copper Fe2O4. We have two examples. These are the two examples. Another, we have symmetry related thermodynamic behavior, in which it is again divided into non-centrosymmetric non-polar and centrosymmetric non-polar. Fourth is structural change during phase transition at Curie temperature, which has another sub classification of three type: order, disorder, and displaced type. Got it? And the composition of Rochelle salt is sodium, potassium, oxalate, dot 4H2. Four water crystallization are there. Next question. Which of the statement is true for ferromagnet? The magnetic field changes always the magnetic field changes always influence ferromagnets. Pyromagnets are in constant dipole moment in their atomic state. The atomic dipole moment is always parallel to the direction of magnetic field, or all the above. They have a constant dipole moment. Second, that is why um, we have polarization, right? Because it has some dipole moment. Dielectric, which show spontaneous polarization, are called as ferroelectric. Your options are pyroelectric, piezoelectric, ferroelectric, or centrosmith. And if you are able to understand this question, then you can answer this also. Or all ferroelectric materials are pyroelectric and piezoelectric. As the name suggests, pyroelectric materials are those materials which change um, in the presence of electric field they behave differently, different thermal behavior. Pyro means heat. Okay, they have a different thermal behavior. And piezoelectric, who will answer the piezoelectric? What is the definition of piezoelectric? Anyone? You understand ferroelectric, you understand, now you understand pyroelectric too. What is a piezoelectric material? It is a material that can produce, it is able to produce electrical energy with as we varies mechanical stress. We have read about mechanical stress, plastic deformation, superplastic deformation, everything. So if this is true, this is true statement. But the vice versa is not true. That is, not every pyroelectric and piezoelectric material is a ferroelectric material. Okay, all ferroelectric material can behave, can produce electrical energy under the variable mechanical stress or under variable heat, but vice versa is not true. Next question. The temperature characteristic of every ferroelectric crystal is called. They behave as a ferroelectric material. The transition is there. So what is that transition? What is the temperature is called? Is it transition temperature, crystal temperature, ferro temperature, or Weiss temperature? So I have already answered it. It is transition temperature. Next question. Which quantity of ferroelectric material varies with temperature in the following graph? It is a plot for a ferroelectric materials, and then we know it has an inverse relation. There's some which property has an inverse relation with the temperature. So this is temperature. This is an hint. What is this? It is at x-axis. What is at y-axis? Anybody? Is it polarization? Is it polarizability? Dielectric constant? Hysteresis loop? It is dielectric constant. And the equation on which it is depend upon is dielectric constant. We have some intercept value, we have some slope value, and then we have temperature. this is that equation. Got it? We have covered number of questions on ferroelectric materials and their properties and their classification. What are they? Examples. Do you have any questions on that? You can raise your hand. There is no problem if you give wrong answers. We are here to discuss, so we can clarify your doubts. Anyone? Okay. So we have another interesting paper as we discuss a lot of research articles as mentioned in your lecture slides. So here is one article from Nature Materials. There is no the date. I have not mentioned the date and the year here, but you can see that the paper is titled as a rhombohedral ferroelectric phase in epitaxially strained hafnium zirconium oxide thin films. Okay. Um, so many authors are involved in this work. So what does it say? Hafnia-based thin films are a favored candidate for the integration of robust ferroelectric at the nanoscale. So what they are basically saying that this ferroelectric material has is a potential candidate if we do it in nanos is a potential nano ferroelectric material. Okay. Um, into next generation memory and logic devices. So they have used in they have used this in they're saying that it can be used in data storage and logic kits. Logic devices, not logic kit, logic devices. This is because their ferroelectric polarization, I'm here reading, if you're following, I'm reading here. This is because ferroelectric polarization become more robust as the size is reduced, exposing a type of ferroelectricity whose mechanism still remains to be understood. So, as we have studied in the properties of nanomaterial, that at the nanoscale, the polarization become much more enhanced. Okay, uh, that is why we were making material in the nanoscale. How how it is different from the bulk phase. Thin films increase crystal quality and therefore needed. We report epitaxial growth. Epitaxial growth is one of the way of synthesis, okay, of hafnium zirconium oxide. This film on 001 oriented, this is a plane. They are saying lanthanum 0.7, strontium 0.3, MnO3 slash strontium titanium substrate. This is a substrate they have used to grow this the thin film of this material. The films which are under epitaxially compressive strain and predominantly one-bar oriented display large ferroelectric polarization value up to 34 micro cent per centimeter square. So from and do not need a wake-up cycling. So what is the takeaway from this line is the units of polarization. What is the unit of polarization? It is charge per area. Here it is microcoulomb per centimeter square and do not need wake-up cycling. Structural characterization reveals a rhombohedral phase different from the commonly reported polar orthorhombic phase. Simple, it's a fact. This finding is a conjunction with the density functional theory calculations allow us to propose a compelling model for the formation of ferroelectric phase. They have used some theoretical calculation to support their experimental data. This usually happens in research papers. In addition, these results point towards thin films of simple oxide as a vastly unexplored class of nanoscale ferroelectric. So this class of material has not been explored much. So this is has a same thing, but it's very much the potential to work upon. Now understand this plot carefully if you do. First see how it is resembling with the one which I showed you. I was not able to make very perfectly, so now you have understood what was the plot look look uh, look like. This is electric field, this is polarizability. Okay, so what do you see on the screen? How these two plot A and B are different from each other. There are some values are mentioned on the point. It is called ferroelectric characterization. Our interest of the plot is that black line. Don't get confused with that um, with the blue line. Our interest, our plot of the interest is that black lines. So see here the diameter or the thin film is, or with the thickness we can say thickness. That is thickness. Sorry, D is thickness. They are saying D is thickness. Here is 5 nanometer. Here is 9 nanometer. So this much. Both are nano, but this has more. It has lesser size. That means lesser size means more more number of grains are there. Area, also the area changes them. Polarizability, as we know, size reduces, polarizability increases. So here P had 18 micrometer and A has 34. So it is matching with the concept, isn't it? First we have read the concept, now we are seeing the proof. And also see what I have told you. Uh, in this, size has reduced, so the coercive force have also increased. This is the coercive force. Here it is 12 millivolt per centimeter. Here it is only if it is 3 we have 6 millivolt per centimeter. Coercive force have also increased. Third point, the remnant polarization I was talking about. What was the remnant? At 0, this is the value. Here what we have, see the scale, it is around 30 micro centimeter microcoulomb per centimeter square. Here it is only maybe about 17 microcoulomb per centimeter square. Okay, so this is the difference between the hysteresis loop of thin film of 5 nanometer scale, 5 nanometer thickness and 9 nanometer thickness. Next part, this is just for your information, you can refer this site. This was just for your information how was liquid crystal were invented, how the concept of liquid crystals came. Okay, so just I will read out to you. The study of liquid crystal began in 188 um, 1188 when an Australian botanist, one botanists are those scientists work on on the plants, uh, flora and fauna, basically on floral creatures, named Frederick Bretzer, observed that a material known as cholesteryl benzoate had two distinct melting points. In his experiment, Retizer Renizer increased the temperature of a solid sample and watched the crystal change into a hazy liquid. As he increased the temperature further, the material again changed into a clear, transparent liquid. Because of this early work, the Renzer is often credited for discovering a new phase of matter called liquid crystal phase. First it was solid, then it turned hazy, then again it was liquid. Is also clear, uh, transparent liquid. Another article which was mentioned in the slider it was from the theory of ferroelectric nanoparticles in pneumatic liquid crystal. If you read this paper carefully, you will understand how uh, the what were the experiments were conducted before they came on to a conclusion that liquid crystals can be used in LCD display. Okay. This was a paper from Physical Review Letter (PRL) and it dated back to 2019. The recent experiments have reported that the ferroelectric nanoparticles have drastic effects on pneumatic liquid crystal, increasing the isotropic pneumatic transition temperature by about 5 Kelvin and greatly increasing the sensitivity to applied electric field. To understand this effect, we developed a theory. They have developed a theory for statistical mechanics of ferroelectric nanoparticles in liquid crystal. This theory predicts the enhancement of liquid crystal properties in good agreement with the experiment. These applications apply even when the electrostatic interaction are partially screened by moderate concentration of ions. So this is how a nanoparticle is there. Nanoparticle in liquid crystal, particle with no electric dipole. It in isotropic phase means they are randomly arranged. Ferroelectric material with dielectric or dipole, which produces when there is an electric field, so they orient themselves in this manner, which is called nematic phase. Nematic means they are arranged along the axis or like along their length of the crystal. One interesting to note that if we read this part, a key question in this field is how to they're telling why they are working on this subject. So it may be of your interest. A key question in this field is how to understand and control the properties of liquid crystals doped with ferroelectric nanoparticle. One paper has argued that nanoparticle produces large local electric field which polarizes the liquid crystal molecule and thereby increase the intermolecular interaction. So they are claiming that one paper is claiming that nanoparticles create local electric field and this affect the liquid crystal. This increased interaction leads to higher isotropic pneumatic transition. So this affect this change if this process increases, then the transition temperature, let me call it transition temperature of a pneumatic crystal increases. It limitation of the now the limitation are they saying the limitation of this approach is that it does not consider the orientation distribution of the nanoparticle themselves. So this is nanoparticle in liquid crystal when no electric moment is there and this is their behavior. So the paper is saying that they have not considered this orientation distribution of nanoparticles themselves. One might expect this distribution to be crucial for understanding how nanoparticles affect the orientational order of the liquid crystal. So if these nanoparticles will orient themselves in some form, suppose this form, then it will affect the behavior of liquid crystals as well. And on this approach, they have uh, studied the statistical mechanics of this. We will not going into the detail, but we are just discussing how they have, what new they are doing, and what was the problem in the existing model. So that is why they need to make a new model. Moving on to the assignment question of week 5. The weight loss versus sliding distance graph at constant pressure for materials, namely A, P, C, and D, are given below. Select the correct option regarding the test. So, which the test they are talking about first? You will be able to answer this question if you know which test they are talking about. Think in which test we discussed the sliding distance and the weight loss. What was that test called? And what was the purpose of that test? It was called pin on disk test. Anybody know the schematic diagram of it? What was the schematic diagram? So I have this disk, motor is attached, some pressure, wait, disk, motor, your sample, and we apply pressure, and it will move like this in circular motion. So what is the sliding distance? The number of rotation it causes, the number of rotation it takes, and when it rotates there is some weight loss. Okay, so now you have to tell which material, this is the plot, which material has the poorer wear resistance. We were discussing the mechanical property while studying the pin on disc. Which option is true? Material A has the poorest wear resistance. Material D can be used for higher wear resistance application. Material A can be used for higher wear resistance application. All the material have identical grain size. See, fourth option is not correct because there is this change in the grain size. That is why these materials are behaving differently and thus having a different weight loss. Consider this 600-meter distance. So D has around 10 mg weight loss. C has around say we have 7 mg weight loss. B have 4 and it has around 2.5 mg weight loss. Okay, this can be 7.5 I say. So that is why if they are having different weight loss, that means the grain size is not similar. So this option is incorrect. Now our we have D of B, A material and D material. So D material has the highest weight loss. That means it does not have a good wearing properties. It cannot give good wear test under pressure. That is why it has a poorest wear resistance. Sample D. So this option is incorrect. This also option is incorrect. And we remain with the option 3. Material A can be used for high wear resistance application. Okay. Which of the following graph correctly represents the pin on disc test result at constant sliding distance in the system discussed in class? You have 4 options. You have to tell which of the graph represent the correct representation of pin on disk test. I have given you the schematic diagram. I have explained you the first question, how the wear resistance changes with the weight loss of all the 4 materials. Then what is the behavior? Tell. So the correct option is with the applied pressure. Option B is correct. We are applying the pressure. We are applying the pressure. Pressure is increasing and more is the weight loss. Okay. But after certain point, pressure no long there is you're not increasing the pressure, but there is no effect on the pressure of the weight loss. The pressure is constant, but the weight loss is increasing. See, this is the plot. Weight loss is increasing. That means here it means that it has completely weared. It has completely failed the wear test. Okay, after this pressure. This is the correct option. Next question. The ASTM standard for pin on disk test as discussed in the class is. So this is a standard machine. Pin on disk test is a standard test. So we have a standard name of the machine. What is it called in the ASTM standard? What is the full form of ASTM? Correct, it is not it is just a theory question. Correct answer is G99. This is a number. All these numbers belong to different tests. So for the pin on disk test, it is G99. Full form of ASTM is ASTM stands for American Society for Testing and Materials. Okay, this is a um, board which gave these standard numbers. What is D? We know that G99 stand for pin on disk test. What does D638 stands for? For which test is it stand for? It is stand for plastic tensile testing. Okay. E8. What is E8 stand for? E8 stands for tension testing. E139 stands for stress. It is for very other very a lot of other purposes like stress test, stress rupture test, conducting creep. These are the words and terminology we discussed while studying the plastic and superplastic deformation. Creep, rupture of metallic materials. D638, plastic. Okay. Moving on to the next question. High cooling rate is preferred for the synthesis High cooling rate is preferred for the synthesis of nanomaterial because it prevents damage of the process, it prevents grain growth.
Grain structure. So yes, you are right.
Yes, so the rate is changes from at this rate it changes 10 raised to power 5, 10 raised to power 7, that is the cooling rate. And the temperature you said 80, yes, it is around 76 degrees Celsius. Okay, from the temperature of 10,000 Kelvin, we are able to uh, prevent the grain growth using this cooling rate. Okay, next question. Clogging and partial melting can be avoided if the particle size is less than 5 nanometer, less than 5 micrometer, greater than 80 micrometer, or in between the 10 micrometer and 70 micrometer. What should be the sample size which you have to put in the vacuum plasma spray technique so it does not clog the and we can avoid clogging and partial melting? What should be the sample size?
Uh, I think among these only uh, one is at the nanoscale level. So other three options are at micro level. So I think it is very hard to judge because in between 10 micron to 70 micron, uh, I think it's greater than 80 microns. Okay. So if I grow something,
You have to avoid both clogging
partial.
and partial melting. We have two different
No, no,
problems
no.
here.
No, the thing is partial melting. So, for example, if in a CVD, if I need to grow something, so my atomic layer should be 10 Armstrong. So, if it is 100 Armstrong, then it is no. Yeah.
So what is your answer? Third option.
So uh, no. You need to. The thing is, if you are growing 10 Armstrong, so it's 100 nanometer or something.
100 nanometer.
No. So and 1 Armstrong. If you are growing 10 100 Armstrong, it is around 10 nanometer. Okay. So in that case also the partial sublimation of materials like the melting and the compound formation is
You have to understand the understand the question from the point of this technique, vacuum plasma spray technique. We are putting some.
I'm actually comparing it with the standard CVD techniques. So I'm just assuming that if I want to grow something, then 100 Armstrong means around 10 nanometers. So it is almost it is barely visible that you are forming a compound. So I think so I think it is very important that what are the what is the dimension of the substrate. If you are simply ma'am, I just want to ask what is the dimension of the substrate.
That is what there is no substrate yet. We have to make the substrate. This technique is used. No.
No. The thing is, I want to. So the thing is, there are A, there is B. Okay, so A and B get reacted to form C. So my A and B are placed now. So A is my separate entity, B is my separate entity. Now, in order to form C, I need to place them very closely and form a reaction environment. Okay, I'm just asking, what is the dimension of substrate B?
Here you need to understand that we are not discussing the reaction part. We are suppose we are having a lead particles, microparticles, and we are bulk particles suppose, and we are changing these lead particle into nanoparticles of lead. So we don't have any A or B reaction. Got it? We are
So
just
so
decreasing the
okay
grain size.
so I think let me clear this. So in all of the options there is only 1 nanometer range, which is I think which is not correct, because most of the particles cannot be formed in that range. 5 nanometer is very small. Okay, so the other is 5 micron. Then micron can be anything. You are not defining the upper range. So I think this questions required some bandwidth of the nanoparticles. Then
So we
another is greater than 80 microns. So I think the option should be four. No, option should be three, not four.
okay. So yes, you are partially correct that you should have a range, and there is only one option which in which range is mentioned. If I use the particles of 10 micrometer and between 70 micrometer, then I will get the nanoparticles of then I will get nanoparticle of some range. But here the question was which bulk particle what is should be the range of bulk particle to avoid these problem. If I use particle size less than 5 micrometer, so it will block some regions of that system. Okay, and if I use particle larger than 70 like 80 micrometer, then in that fraction of time it will not partially melt, and it will not partially melt, then plasma will not be the plasma which is created will not be uniform, and when it falls on that substrate or where it is getting collected, we will not get a uniform target. The target will be of will have nanoparticle, but it is a collection of nanoparticles. So that is we are talking about sample in the bulk phase, not in the nanoparticle. After the nanoparticles have been grown, then we can use that in CVD method. The target which you have in CVD method has already has nanoparticles. Hope you have got the question.
I think in plasma spray technique, you want me to explain that. there is a certain amount of nozzle which is required
Yes.
for these materials to just spray at the
Yes.
sublimation temperature. This is what you
Yes.
mean. So it's
Yes.
a okay. So it's not a dimensionality problem. It's a technique problem that you need a
Yes.
specific range of nanomaterials for a jet to
Particles.
spray, right?
Microparticle. Yes.
Yeah. Okay, fine, got it.
Yes. So moving on to the next question. Barium titanate shows ferroelectric behavior due to lattice expansion, a net difference in the magnitude of positive and negative charge, displayed center of positive charges from the center of negative charge, or more number of oxygen atom. You have to tell me the reason why barium titanate has a ferroelectric behavior. What is the reason behind it? What is the condition for the ferroelectricity? There are basically two conditions for the ferroelectricity as discussed. Two conditions are, let me write it again. The first, there should be charge neutrality. That is the basic condition. And second condition is the center of positive and negative charge is not coinciding. Since it does not coincide, there is a there is some net dipole moment. And this dipole moment in the presence of electric field creates polarization, permanent polarization. Therefore, the option 3 is correct. Difference displays center of positive charges from the centers of negative charges. Next question. The advantages of using nano ferroelectric material in LCD is we use ferroelectric material in LCD displays. So what is the purpose? Response time reduces, we have fine pixels or reduced power requirements or all of the above. We can use ferromagnets, but there's a proper reason that why you are using nano ferroelectric. Anyone? Which of the options are correct?
All are correct only, ma'am.
Sorry?
All of the above because it reduces the power requirements and it reduces the time and it gives fine pixels also.
Yes. Because when we use nano ferroelectric with liquid crystal, it is able to give the lesser response time. So that is why all the options are correct. Ferroelectric storage will require less energy than the ferromagnetic storage. True or false? You can get your answer from this question if you have understood this. Ferroelectric storage will require less energy than ferromagnetic storage.
True, ma'am.
True.
The reason is there is a permanent dipole in the system. So due to the net charge displacement, so I think ferroelectric storage will require less energy than ferromagnetic.
Yes,
Behavior.
correct. The statement is true. Ferroelectric material shows spontaneous polarization. True or false? It is a definition based question. Ferroelectric material show spontaneous polarization. This statement is true. Yes, they show polarization.
I'm not getting spontaneous. There is polarization. What do you mean by spontaneous?
Uh, Spontaneous polarization means that they have polarization. I agree with you, but in the presence of electric field, the polarization increases. If you see this plot, E versus P. Okay, that is it is meant. It is an incomplete question, but this is it. This is the meaning. High velocity of the particle in vacuum plasma spray technique helps in grain growth. True or false? Does there does is there any effect of the velocity of the particles on the size, on the grain size of the nanoparticles? Do you think so? There should be an effect. There should be an effect of heating. There should be an effect of cooling rate. But is there some effect of velocity of the particles? Is this statement true or false? This is false. There is no such effect of velocity of the particles. Okay, so we have completed with the ferroelectric part and the assignment question of last week. Now we will discuss the concept and the problems of the this week's lecture. So tell me types of band gap in insulator, semiconductor and metal, and the equation related to the band gap. Define related equation. So I'm drawing some band diagram, so you have to tell me which of the band gap belongs to which type of material. Conduction band. This is conduction band. This is valence band. And so A belongs to which type of material? Is it an insulator, semiconductor or metal?
Uh, so less than 2, it's a semiconductor.
Yeah.
Semiconductors.
Yes. Right. Then B.
B is metal, ma'am. It is either it will have partially filled or overlapping. It will be metal.
Yes. So which is the case? It is partial filled or is it overlapping? Which case of the metal is it?
It is
Is it
filled only,
overlapping?
overlapping.
Yeah. C.
C is a insulator, greater than 2 electron volt.
Yes. Now this is insulator. This is metal. And what is the equation related to the band gap?
Eg equal to H mu.
Yes. And if I want to reduce F, mu, can you simplify it? This is frequency, right? What is H?
H threshold value or a threshold value or transition state.
It's a Planck constant.
Threshold
Yes.
value.
H is Planck constant. It is a constant. E is energy. What is the value of Planck constant? What is the value of Planck constant?
Do you want me to express in joule per hertz?
Yes, in joule you can tell.
It's around 6.626 into 10 raised to power minus 34
Yes, 34.
joule per hertz or something.
Yes,
Yeah.
6.6626 10 raised to minus 34 joule per second, right? Joule hertz. That's the value of Planck constant. This equation we will use in the upcoming numericals. So if I want to simplify E is equal to h mu, we can use h into frequency can be written as c by lambda. Okay, c is the speed of light. Fine. Next question. How can you influence band gap? So the question means you have same material. Suppose we have, let's take strontium titanate. We have to keep composition same. We have to keep um, structural parameters same. Everything should be same. Then uh, chemical composition, everything should be same. But we have to influence the band gap. That means you have to reduce the band gap. What are the factors you have to play with in order to reduce the band gap? What are the factors you have to keep in the mind? We have studied three factors in the lectures. What are those factors? Porosity. Porosity affect the band gap. Defects. Introducing defects into the system. Third, what is the third factor?
And porosity and effects are the completely different entities.
Yes, they are
So,
different.
so you are talking about defects in what, like introducing some atoms or other materials into the system, or just interstitial defects or interfacial defects.
Defects can be introduced. Uh, not defect can be introduced when we're not. I'm not talking about interstitial or other effect. That is introduced when we do substitution or we remove some atoms or we create vacancies.
Yes, yes.
Def-
So you're talking about that, right?
no, I'm talking about defects. Even when we reduce the sizes, there is some
Defects in the defects in the sense you're talking about the same material, but the same
yes,
material is not present at the same time. Like there is a varying composition of materials throughout the lattice structure.
yes. So when particles are changed into the nano size, there is some change in their lattice parameter. Okay, so this creates some defects. Surface defects are also there. So in that also can influence the band gap. What is the third factor on which we can influence the band gap? Porosity is there, defects are there, grain boundaries. It means just we have to reduce into the nano size. Okay, grain boundaries increases when we increase the when we decrease the size of the particle, right? We have lot of grains. That means we have lot of grain boundaries, and which will affect the band gap. Now it is a numerical based question. Calculate the energy of visible region. We have two values. Lambda is given to you and you have to calculate their energy. You can use this formula into c by lambda. So you know the value of lambda, 6.626 joule hertz. It is, we can write hertz as joule second. Now what's the speed of light? Speed of light is 3 into 10 raised to power 8. I'm just telling you the approximate value. Meter per second. You have the lambda, which is 400 nanometer. Will convert into meter. So do this calculation and tell me the answer. 6.662 into 3 divided by 400. We will get the values 0.049. Now we have minus 34 joule second meter per second and 10 raised to power minus 9 and here also 8. So meter. This will get cancelled. This will get cancelled. 0.049 minus 34. I hope everybody is following the solution. Plus 8 plus 9. 10 raised to power 17 joule. But I have to convert, if I want, this is joule. I want to convert this energy into electron volts, because since we are talking about band gap. Okay, so band gap is mostly represented in electron volt. So 1 joule is equal to 1.6 into 10 raised to power minus 19 joule. So what we will do? Minus 19 and into 1.6. It is 0.0784. So what is the value? 0.0084 electron volt. Okay. Similarly, you have to calculate the lambda value for the energy value for the 700 nanometer. Okay. I hope everybody is following. Next question. What is the quantum confinement and how does it affect the band gap of nanomaterials? Here what we have to discuss this part. How the grain boundaries affect the band gap and how it is related to the quantum confinement. Can anybody explain? Yes. So quantum confinement, if we suppose we take a particle of this size and we take a particle of this size, and we know uh, when when an electron moves from valence band to conduction band, we have electron and hole pair generated. So this distance is called exciton. This distance is called exciton. This is called exciton pair, and the distance called exciton distance. This is a particle and there is some transition in it. And if this size of the particle is greater than its exciton distance, then uh, there is no quantum confinement. Okay, and we get a quantum continuous uh, continuous layers of energy. Okay, we cannot distinguish between the layers because there's a continuous arrays are there. Whereas if we take a quantum dot or a nano sized particle, the exciton distance remains same, but since the size of the particle is less than its exciton distance, it get confined within that range. It want to expand in this manner. It want to increase the distance of conduction of hole and electron, but since the size is small, it will confine itself into that distance. So this is called quantum confinement. And what when this happens, the band gaps we have distinguish band gaps. Not like arrays of energy level, we have distinct energy levels. Able to uh, uh, distinguish between each of the energy level. Got it? So this is the case of nanomaterial and this is the case of bulk materials. Got it? You can raise your you can uh, if if you have followed, you can give a thumbs up also. So I will understood you have followed it.
Yes, ma'am, we are
Yes,
following.
ma'am. Understood, ma'am. Understood, ma'am.
Okay. Now we'll move on to the next question. Explain the instrumentation of XRD machine and on which law does it work. So this is a technique which is discussed in the lecture. We have discussed the technique like SEM, PEM. Okay. Now we have to discuss another characterization technique, XRD, which is called X-ray diffraction. So I will draw some figure and you have to tell me which is the source, which is which side should be the sample. Here it, it is falling and here it is. We have planes. Sample is like this and we have multiple planes over here. So A, B, C. Which of them is a source and what is the source? What is the source? A is source.
A source, ma'am.
Yes. And what kind of source is what is the from which material, what is the material it is used, we are using to have to generate x-rays. Source is generating x-rays. Agree? These are x-rays.
Yes, ma'am.
Okay. So what is the material from which x-rays are generated? Do you know? So we have lot of material in our periodic table. Sodium, titanium, copper, zinc, molybdenum, nickel. Which of the element is used for generation of X-ray source in XRD? You can give a guess also. There is no problem. If you do not know, you can give wrong answers also. We are here to discuss.
Sodium.
No, not sodium.
Copper.
Yeah, right, copper. Any other?
Maybe titanium.
We need a heavy atom like copper. See,
Titanium, ma'am.
uh, no, titanium is not. See, you're given example of copper, right? Copper is in the right of the periodic table. Somewhere here, copper is lying, and titanium lies over here. So, if copper is being used, so if you have a general idea of periodic table, then the elements around it will have a similar properties, right? Material around elements around it will have
Actually,
be.
there were few. I don't know many, but there were few like iron you can use, silver you can use, cobalt
Yes,
extent, copper is the most common
yeah,
we are using.
heavy metals are used which lies near to the copper. Molybdenum is one of them.
I don't know about the molybdenum, but silver I know. People use iron and cobalt too. But silver I know.
Right. Yes. We generally use copper metal as for the X-ray generation. But molybdenum is also used when we are dealing with the crystal structure which has much more heavier atoms. Suppose if we are using with the suppose heavier transition series, say prosodium, lead. Okay, in that case, to understand, since the scattering is very high in case of these heavy metals, that is why we use molybdenum X-ray source. So now just coming putting our discussion to copper. So copper is used. Okay. Now which of them is a sample? B is a sample or C is a sample?
B is the sample, ma'am.
Uh, can you give any example for the samples? Samples. What kind of samples we use in XRD? What samples can, according to you, which type of samples can be used? Can nanoparticles be used to study their X-ray pattern? Can nanoparticles be used?
Yes, yes, ma'am. Nano crystalline materials can be used or metals can be used.
Yes, metals can be used. What about bulk material? Can we use bulk material and study their XRD pattern? Bulk like material in range of micrometer, particle size which are having in micrometer, can we use them?
Yes, ma'am. Yes, ma'am. We can use, ma'am.
Right. So we can use range of samples. Can we use liquid samples? Can we use semi-liquid samples in XRD?
No, ma'am. It should be in powder form only.
Uh, Earlier we were able to study only powder samples. Now we are having sophisticated instrument, very advanced instrument. So we can use liquid samples and semi-liquid samples. Okay, we can use
Okay, ma'am.
we can take XRD for of butter, oil, etc. Okay, so now there is no any such limitation. And C is A is
Detect.
source. Yes, detector. Okay, this is a schematic diagram for to understand the XRD pattern. XRD instrumentation pattern is different. So on what law does it work? What is the law it is called? What is the name of the law?
Bragg's law.
Right, Ragg's law. And what is that equation? What is that law says? What does the law says? It is n lambda is equal to
N lambda equal to 2d sine theta.
2d sine theta. Now you understand this diagram? Tell me uh, the lambda should be the lambda which is used in the Bragg's law belongs to the sample, or this is, if I'm using the lambda of this of the incident ray or a reflected ray. The lambda belongs to which? Does it belongs to source? Yes or no? Answer this first. Does lambda belong to source?
Yes, ma'am. Belongs to
Right.
that X-ray source only.
Okay. And what is our source?
Monochromatic light
Mono.
or something.
Yeah. But source is copper, right? Copper.
Copper. Yes, ma'am.
And now we have talked about monochromatic. What do you mean by, it is a good thing you know this. What do you mean by monochromatic source?
Like the source of light through it passes and it will uh, spray on that sample. It will reflect on that sample. Through lens, it will be sent to that sample, that light.
Yes, light is sending. But why we need to use term monochromatic copper source? What do you mean by monochromatic? No, your answer was not fully right. Anything else is in your mind? Monochromatic means, so we use copper as a source, right? So copper gives two kind of wavelength, copper K alpha and copper K beta, depending upon the energy level from where the X-rays are ejecting. Followed? Got it?
Can we please, once again, please.
Yeah. What? Like,
For that monochromatic, you told na that K alpha, that K beta.
I'm not given the answer of monochromatic. Yes, I'm explaining you. Do you follow this? Copper, when you use an X-ray source, it gives two kind of radiations, two kind of wavelength. K alpha, that is called, one is K alpha and one is K beta. K alpha and K beta are named on the basis of the energy levels from which the X-rays are generated. We have different energy levels in an atom, right? K, L, M. Okay. If it generated from L shell, then it's called K beta. If it generated from K shell, then it's called K alpha. Followed?
Yes, ma'am.
Right. So, if we use these two rays in the X-ray source, then we will have two different kind of, this is a XRD pattern, right? This is a XRD pattern which you get. If I use these two source, then I will get once one peak related to K alpha and another peak beside this related to K beta. Okay. If this is my XRD peak and I'm using both the radiation, then I will have one for K alpha and one for K beta. But you want to study the property of the material, not the source. Okay, this is the interest. This is our interest, not this is the interest. In order to simplify the XRT pattern of the sample, we need to remove one of the wavelengths. So we remove K beta. Okay, we remove K beta and we are remain with K alpha, and this is called monochromatic. Only one, mono means one kind of radiation is allowed. Wavelength, wavelength of radiation is allowed. Followed? Understood the meaning of monochromatic?
Single wavelength we are using.
Yeah, right. Single wavelength we are using. And that is the wavelength is the 1.54545 Armstrong. Got it? This is the meaning of monochromatic. And how do we remove K beta? We remove using nickel. Nickel grating. Like we have nickel crystal arranged in kind of grating. If you know grating, like uh, they are like one plane on the other, slanted. Okay. If you Google the picture of grating, you will understand. We use nickel grating to remove K beta. So this is the definition. This is the definition for the Bragg's law. Do you understand lambda now in the Bragg law?
Yes, ma'am.
We use 1.45 Armstrong if you are using copper source. If you use molybdenum, nickel or cobalt, this value will change. Fine. What is N? N is the order. That is it falling on the first plane, or is it falling on the second plane or third plane? Okay. So we generally take N is equal to 1. Okay. I will explain why we take 1 in the next class. Just before our aim is to understand the law first. Okay. What is D? What is D?
D spacing.
Yeah, but what is D in this diagram? What is the D? Where should I write D? Where should I mark the D? D spacing? Yes, spacing of what? Spacing of what?
The two parallel lines.
Parallel planes. These are planes. Okay.
Parallel planes.
Distance between two planes. Parallel planes. D spacing. Theta. Theta. Where should theta lie? If this is the okay, this arrangement is called Bragg Bretno Brett Brent Brento Bretno arrangement. Sometimes in this right now our detector is moving. Okay, when we use the XRD technique, sometimes source moves, so that arrangement is different. Here we are discussing the arrangement of this kind, so this is called Bragg Bretno arrangement. So the theta is this one, this theta. If this is a plane, so this is the theta, 2 theta we call it. Okay, this is 2 theta and that theta is used over here. This is called Bragg's law. Now you understood. And if you are very if you have much more interest in the XRD, then you should search on the internet who discovered XRD. Okay, who on which scientist this Bragg's law is named, and you will find one interesting thing. You will find his father was also invented X-rays, and his son invented XRD machine. Look, the Bragg's law, which led to invention of XRD machine. Do you follow this? Have you followed this? His father was Lawrence, and his son Henry gave this Bragg's law. Okay, now we will study further. We have not covered all the concept in this class. We will study further concept in next class and discuss the assignment problems as well. If you have any doubts, you can tell and we can discuss it. Otherwise, we can
Ma'am,
finish
in
the.
the sum, I have doubt, ma'am, that calculate the energy of visible region. For that H
Okay.
value, 3 into 10 to the power of 8, ma'am.
Sorry, H value. What? I didn't follow. What is H?
No, that
Please.
sum calculate the energy of visible
Ye-
region,
Yes.
400, ma'am.
Okay. So
I
what is
just
the?
want to clarify that one, ma'am.
Yeah. What is the doubt in this problem?
That lambda value is 6.626 into 10 to the power of minus 34, na, ma'am.
This is H.
Okay. That C value, speed
This
of
is
light
C.
is 3 into 10 to the power of 8.
Yes. And this is lambda in nanometers. So I have because all the units are in standard SI units, meter, joule. So I have to convert into the meter.
Oh, simple,
This I yes I have
simple calculation, we can get that answer, ma'am.
right. I have put H value. You know C value. I have given you lambda value. Simple multiplication and divide.
Okay, ma'am. I will try, ma'am. Thank you.
Okay.
Thank you.
Yes. Welcome. Thank you.